I'm going to do some algebra. Yep. I'm going to do an algebraic move. You could call this one maybe a trick. I don't know. It's not that tricky once you see it, but I'm not quite sure it's something you would think to do right away. I'm going to write kind of in slow motion here. And let's see if someone can figure out what I'm doing. I know I'm writing on the board, but there we go. I'm going to come in with the conjugate. But I can't just throw the conjugate there. I have to throw a 1 here, don't I? And so it can only be the conjugate over itself. See, here's my 1. I've decided to multiply this by 1. And the 1 I picked is just the conjugate. Why? Because the conjugate's always been good to me. And every time I've ever broken it out, it's never failed me. So this time I'm going to bring it in again. And let's just see what happens, right? This is that whole, step up to the plate, take the swing. What are we going to do about Super Bowl Monday after Super Bowl? Are we all going to be okay getting here at 9 o'clock on Monday? Probably not. He's talking about, yeah. All right, so how many of you are going to watch the Super Bowl? Okay, that's not enough. I was going to cancel class, but that's not enough. I'm just kidding. I was not going to cancel class. All right. How many of you are Patriot fans? How many of you are for the Eagles? Okay, and then the rest of you don't care? Okay.
I think it's something tearing at the soft underbelly of our society.
What is?
Football.
Football is tearing at the soft underbelly of society. I would counter that with, I can't imagine our society without sports. What would people do with themselves? I just think about all the people that rely on it. Well, I'm just saying, that's always been, for me, it's been like, I've thought about this a lot. It's like, I don't want to take sports away. Now, I do think that athletes are overvalued, but they're overvalued for a reason, because people watch, and people look forward to that. I can't wait till next fall. There are like huge masses of people that creates a happiness in their life. Yes, I can't imagine the world with a bunch of those people walking around unhappy. Okay, let's get back to this. All right, here we go. Here to here. We have enough miserable people. There to there.
X squared plus 4.
X squared plus 4. The roots hit each other, they go away. Now, do I need to concern myself with the middle terms? The middle multiplications are going to cancel. So all I really care about is the last one.
Minus x squared.
Minus x squared. That's it? That's what the top becomes? Wow, okay. And then the bottom is this times 1, which is itself. Now, what have I gained? Have I gained anything? Are things better? Is life better here? These x squareds cancel out, right? Which is nice. I'm left with a 4 on top. So the top is actually headed to a fixed number. And the denominator is now what is the denominator? It's not infinity minus infinity anymore. It's infinity plus infinity. And infinity plus infinity is infinity. That there's no argument. See, when you have subtraction, you can never tell who's going to win because you don't know which one's bigger, right? But if I say take a huge positive number, add it to a huge positive number, there's only one result, a huge positive number. So this is infinite. Now you have fixed over infinity, not fixed over 0. Fixed over infinity goes to 0. Agreed? So this limit is 0. So if we were to take bigger and bigger values of x, if I graph that, bigger and bigger values of x, the graph would start to taper off towards the x-axis. I think I said y-axis earlier when I was talking about horizontal asymptote. I might have said y-axis, oh well. Good? All right, so our answer is 0. So the conjugate's in play. So when you have infinity minus infinity, we've seen these done two different ways. I factored, and then I also did a conjugate. Let's do one more. One more of these. And then we'll move on to the next section. Limit as x goes to infinity of x to the 2/3 minus x to the 3/4. This is a tricky problem. And I've been known to give one like this on a test. Not to trick you, but because I show you one and I expect that you can do it now, you know? So what's happening here? X is getting very big. X raised to the 2/3. Still getting big. What does raising to the 2/3 really mean? Raising to the 2/3 really means I'm taking what root? Cube root, and I am taking the x and squaring it. That's what that really means. Okay? So if you look at it this way, it's becoming infinite, you're squaring it, huge, cube root of a huge number is still a huge number. So it's big. This is infinity minus infinity again. Now, I'm not quite sure a conjugate's going to help us here. In fact, I know a conjugate's not going to help us. So let's try this factoring game. All right? You ready for this factoring game? I'm going to pull a GCF, greatest common factor here. But those fractional exponents should actually confuse you a little bit, which is why I gave them to you. So watch what I'm going to do. I'm going to just do algebra over here. I'm going to leave that limit alone. This is scratch work on the side. X to the 2/3 minus x to the 3/4. If I have any hope of pulling out a greatest common factor, I'm first going to rewrite those fractions with the same denominator, a common denominator. So what is a denominator that these both could have? 12. 12. Let's rewrite it. So that's x to the, so I multiply top and bottom by 4 here. So I get 8/12. 8/12 is still 2/3, right? Minus x to the 9/12. So algebraically, that's the same thing, isn't it? And I think at this point, we can probably see maybe what they have in common. If this has x to the 8/12 and this has x to the 9/12, what do they have in common? It's kind of like if I write x squared minus x cubed, you say they both have two factors of x, right? They both have 8/12 in common. Let's see if that makes sense. If I factor out x to the 8/12, what would I have? What do I have right here to get back this? 1 minus, now here to here, I need x to the 9/12. So I need x here, and then what power do I need here? So when I multiply by this, I get 9/12. 1/12. Why 1/12? Because when you multiply these two together, you're going to add the exponents. When you add the exponents, 8/12 and 1/12 will give you 9/12. Make sense? Okay, now if we come back here, limit x goes to infinity, and rewrite it, I'm going to leave it as 8/12. I realize you could reduce that fraction, but I'm going to leave it as 8/12 because I don't need it. I don't need to reduce it. I can tell you what's going to happen right now. Where's this thing going? This is going to infinity here, right? That's infinity. So it's infinity times, and that's the key. This is now multiplication. Here is 1 minus infinity. 1 minus infinity is negative infinity. So you're going to be multiplying that by negative infinity. See? Multiplication instead of subtraction. And a positive number times a negative number is negative. They're both huge, negative infinity. Okay. This makes sense over here, what I did? There's other ways to do it, but I like this way. You get a little common denominator, factor out, you're done. All right, we got about half an hour. You all doing all right? Unless, let me double check my notes. This should complete the section on limits at infinity, or infinite limits. Remember that there are two types of limits in this section. We spent almost a full day on each one, on each of the types. So we did something like that. Yeah, I think that one's worth talking about. Yeah, and then we'll have a little summary. So 2 more limits for us to look at. Limit x goes to infinity of sine of 1 over x, and the limit as x goes to infinity of sine x over x. These are 2 separate limits. So let's just look at the first one, and let's see what happens as x goes to infinity. As x goes to infinity, what does 1 over x go to? What does this 1 over x go to as x gets big? 0. That's that special property, right? You have 1 over x to a positive power. So this thing inside here is going to 0, isn't it? And then you're taking sine of that. And what is sine of 0? 0. So this limit is just headed towards 0. See, there's no work really to be done there. Now, what if this would have been, I guess I'm giving you another example. What if this would have been cosine instead? That would have been headed towards cosine of 0, which is 1. All right, let's get to this one. Do you recognize this? Sine x over x? That should be 1, but I said to be careful that it's only 1 when? When x is going to 0. When x is going to infinity, something very interesting happens. And this is actually a really important function. Tell me about the form of this limit. Where's the bottom going? Because that's the easier part. Infinity. Now what about the top? What does the sine function do as you head out to infinity? What's the sine function look like? It's just going to go like this, right? That's all it's doing? So as we move to infinity, the top just keeps on, the numerator keeps on going back and forth between -1 and 1, right? Well, then you could almost say that, and I haven't used this word yet, you can almost say that the numerator is bounded. Couldn't you? Bounded? What is it bounded between? -1 and 1, right? So imagine your numerator is sitting there, between -1 and 1, and your denominator is just getting huge. What's going to happen? What do you think is going to happen? It's still going to oscillate, but here's another way. Here's another way to think about it. Do you remember this from pre-cal? I'll use that. What was the number out in front of the sine? If you were asked to graph a sine function, maybe I'll use a lowercase a. What was the number in front of the sine? This number right here. Amplitude. Good. Do you remember that number out in front of the trig function for sine and cosine was the amplitude? And if that was a 1, then the amplitude was 1, so it was between 1 and -1? Yes? Yes. And if I changed that to 2, it would change the amplitude, 3. Or if I made it a half, it would get shorter? Yes? Okay, let's look at this function again. Could you look at this as this instead? Is that the same thing? Sine x over x is the same as sine x times 1 over x, because that x would just slide under there. Do you agree that that's the same? So couldn't you look at that almost like you did in pre-cal, where the number in front is your amplitude? So what's happening here is this is your sine function, right? It's wanting to go up and down, and this is your amplitude. But as x gets huge, what's happening to this number? It's getting smaller, isn't it? Headed towards 0, which means that you're trying to draw sine curves with smaller and smaller amplitudes. So your graph looks something like this. Like that.
Does the period change or does it stay the same?
The period should be the same unless we change something in here.
Just the decrease?
It's just the height. It's shrinking as we go. All right? Does this kind of make sense? So it's headed towards where? 0. The amplitude is, well, I don't want to go too far into this, but I think this is such an important thing. Let's first determine, let's just say that the answer is 0, okay? Just from what I've explained here. Mm-hmm. We have already discussed that if your numerator is fixed and your bottom goes to infinity, it's 0, and everyone's been happy with that. What I'm now here to tell you is that it doesn't even have to be fixed, it just has to be bounded, stuck between two things. Like a sine curve is stuck between two things. As long as the numerator is bounded and the denominator goes to infinity, you're going to go to 0. Your limit's going to go to 0. All right? Now, let me see if I can show you something. This is really cool. I think it's cool. I don't know if you will. Let's look at this function. F of x is 1 over x. Okay? It looks like this. Right? That's what 1 over x looks like. Yeah? Now, I'm going to take this part right here in the first quadrant. I'm going to reflect it down. That would be the reflection of 1 over x down here, wouldn't it? Okay, now what I'm going to do is I'm going to draw a sine curve that has as its amplitude 1 over x, because that's the amplitude of this, right? And here's what it would look like. Okay, so what's happening here is you're getting what's called a dampened oscillation, a dampened sine function. It's trying to be sine, but it's forced to stay between these two. And so it just kind of vanishes down to 0. Now, why would that be useful? Well, in the real world, if I'm trying to describe an object, right, like let's say a basketball, and I drop it, it's going to bounce, come back up, right? And then bounce, come back up, bounce, come back up. And that's going to be like kind of like a sine curve if you wanted to. But a sine curve by itself wouldn't be good enough, because that would mean the ball needs to come back up to where I dropped it from, right? Exactly where it dropped from, and then come back up, and then go back down and come all the way back up, and not lose any of its energy. And it's impossible to create anything in the real world that preserves all of its energy like that. So you lose energy in the bounce, and it doesn't come up as high, right? And then next bounce is even lower and lower and lower and lower, and eventually it's just and then nothing, right? And this is a great model for that sort of behavior. So you would be more likely to use a dampened sine function in a physics class than a true sine function. But you need this to start, right? You got to have a starting place. And you can control this because maybe you make it x squared instead. And then your dampening happens even tighter. So it makes it dampen faster. Or maybe you even use something crazy like e to the x, which gets huge fast. And so that forces your dampening to happen even quicker. And you can make all sorts of tweaks to this to make it model your real world situation. I have an 8-year-old daughter, and she got one of these really, really super bouncy balls, you know, the ones where like you throw them, they're like, off the walls and everything in the house, right? You know what I'm talking about? So she's like, this is so bouncy and all this stuff. I said, I want you to hold it out, and I want you to let it go and keep your hand there, and do you think it's going to come back and hit your hand? So an 8-year-old's mind, they throw this ball, they see it go bouncing everywhere. They think that when they let it go, it's going to go back up higher. And I finally convinced her that, it's never going to come back up and hit your hand, ever. You're always going to lose some of it. What is it lost in? Where does that energy go? It doesn't come all the way back up. The air does slow it down. What if there was no air? Would it come all the way back up?
Not necessarily. It would have a difference.
If there's no air, would it come all the way back up? No.
Lose on impact.
You would lose it on the impact, but in what form are you losing?
If there's no atmosphere around it, like a lot of rules just kind of fall apart.
Okay, so if there's no air, when it hits the ground, the ball's actually going to deform. It's going to deform. It's going to be very microscopic, but it will deform. And to deform it, that is a conversion of energy, and that energy goes into heat. So it actually moves the rubber ball. It moves a little bit, and you actually, moving those molecules creates heat, and that's loss of energy right there. And so it will never come all the way back up. You can have a theoretical ball that could come back up, but you could never have a real physical ball come back up. Anyway, this is not a physics class, but dampening oscillator, so very important function, these type. Most energy is lost in heat. Mostly everything that we lose in, as far as energy and efficiency is in heat. All right. So here's a summary, and this is our first version because we're going to add more to this later. A summary of what we've done so far. Numerator, if your numerator goes 0, denominator goes to 0, then you must do some work, right? If your numerator or denominator go to plus or minus infinity, then you've got to do some work, right? If your numerator is a constant and your denominator goes to 0, it's either going to be infinity, negative infinity, or it doesn't exist. If your numerator goes to 0 and your denominator goes to a constant, it's just 0, because you're not getting 0 over 0, right? I say here non-zero. Top goes to 0, bottom goes to 5, answer 0. If the numerator is a constant and the denominator goes to positive or negative infinity, that goes to 0. That's what we were just doing. If your numerator goes to infinity and your denominator goes to a constant, this goes to infinity or negative infinity, depending on the signs of things. We did one of those. And then this is that last one we just did. If the numerator is bounded and the denominator goes to positive or negative infinity, the limit's going to go to 0. Okay. And people will ask, can we have a cheat sheet for the test and stuff like that? You need to know those. And again, it's not because I'm trying to get you to memorize. I'm not a big memorize person. In my Cal 3 class, on their final, they have like 20 pages of formulas. It's a huge amount of formulas they have to memorize. This is not really formulas. These are ideas. These are concepts. You need to understand what's going on. Oh, top's going to a number, bottom's getting big, that ratio gets small. That's understanding as opposed to just brute memorization of stuff. With me? So give yourself some time to absorb that information, and we're going to move on to continuity. All right. Continuity is kind of a weird section because continuity is like extremely important in mathematics, but it really doesn't play a huge role in your ability to get an engineering degree or to move on in calculus. But it is a very important property of functions if you're looking at it more from a pure mathematical perspective. So I don't really emphasize this section heavy. You can survive without really knowing the true meaning of continuity, but I think you'll do all right. We'll see. So a function is said to be continuous at a point A if the limit as x approaches a of f of x equals f of a. That's it. That's what it means to be continuous. Make sense? No. So I'll show you with a picture. It's a very, very simple definition. There's no more bells or whistles to it, all right? It says this. If you have a function and you go to some point A, we've learned here that at A, the function could have a hole, right? It could be undefined. And then you could come in from the left and right, and it could do all sorts of stuff, right? But what if we come in from the left and the right to the same place? We would say that the limit exists, right? The limit exists. But at A, it would be undefined. What if I fill this in right here? Would this limit still exist? So the limit as x approaches A of this function, does it exist? Yes, because from the left and the right, it's going to the same place. Yes? Now, what is f of A? Well, let's just make this, let's call this L, and let's call this M, okay? So this right here would have been L, right? And this right here would have been M. Agreed? This is not a continuous function at A. It's not. The definition for continuity is this. Continuous at A means this. Limit as x approaches A of f of x is equal to f of A. These two are the same, is what this is saying. That's what the definition of continuity means. So if I were to try and want to fix this to make it continuous, what would I have to do? I'd have to erase this dot and fill it in, and I wouldn't have options. It could only go in one place. Now, that is a continuous function at A, which most of the function you've studied in your whole life have been continuous, okay? But it's not a given. Not every function behaves that way. Make sense? One way you could look at this is as follows. Let me give you a couple examples. Is that function continuous at A? No. Why not? Why is this function not continuous at A?
It stops at A and then it restarts again.
Okay, but say it in terms of calculus. What is wrong? What is breaking down in this?
Well, that says it's continuous and it stops. So if it was continuous.
No, but in terms of, use calculus language here. The what? The limit doesn't exist. That's why this isn't continuous. It's not because it's not defined. It's defined at A, isn't it? The problem is the limit doesn't exist. The limit doesn't exist because the left and right sides go to two different places, right? Okay. There it is. Is that continuous? Why not? Does the limit exist? Does the limit exist? The limit exists. From the left and from the right, it's going to the same place. But what breaks down? F of A is not defined. Okay? So that's not continuous. How about, okay, so it wasn't defined. How about that? So like I showed you earlier. Does the limit exist? Is it defined? Are they the same? No. This is not continuous. Right?
Yes.
So what we need is for everything to come together at the same point. Now, if I'm trying to tell my 8-year-old daughter what a continuous function is, which I haven't, okay? But if I were to try and explain it to her, one way I could explain it to her is that a continuous function can be drawn without picking up your pencil. As opposed to a discontinuous function, you must at some point lift your pencil up and then continue. Here, I'd have to lift my pencil up and then continue, right? Here, go fill it, come back, continue. So that's a very childish but convenient way of thinking about continuity, is that it allows you to draw your draw your graph without picking up your pencil. That's continuity. That's what it means to be continuous at a single point A. Okay, so I can move over to the side just a little bit and try another one like B and go up here. Look at that point right there. Would I be continuous at B? Yes. And if I moved over here to C right there, would I be continuous there? It's supposed to come out. Yeah, it looks good, right? No breaks. How about on this one? If I let this be b, do I look continuous there? Yes. So it's only places that we have breaks or jumps or missing points, right? That we have these places where we are not continuous. You get the idea? So this is not continuous? It's not continuous at 2. That's what you could say. At 2, it's not continuous. Everywhere else, it's continuous, right? Still not continuous at 2. Continuous at 2? Continuous at 3? Yes. So we have an idea of continuity. Discontinuity is just a function that is not continuous at a certain point. So when we come back here and we say, is this function continuous at 2? Yes. Is this function continuous at 2? No. So we could say that this function is discontinuous at 2. That's the way we could say it. Instead of saying not continuous, we just say discontinuous. But that's a technical term that we use. Is it making sense? Let's not overcomplicate it, all right? I talk about drawing pencil. There are 3 types of discontinuities. There's jump discontinuities, infinite discontinuities, and removable discontinuities. All right. There are 3. Jump, infinite, removable. I'm saying it again because you look like you're falling asleep. This is important. These 3, don't forget these. So here's an example of a jump discontinuity. It's happening at 2. I have a jump in the graph right here. Draw it, pick up your pencil, move it. You jumped, right? Infinite discontinuity. That's almost like a vertical asymptote, right? However, at the vertical asymptote, my function is defined. So you actually have this going up to infinity, this going up to infinity, but at 2 you're defined, but they're not going the same place. So this would be a discontinuity at 2, but it's called an infinite discontinuity. The third type is called a removable discontinuity. Anyone have an idea of why they call it a removable discontinuity?
Because they removed the point.
Because they removed a point? Yeah, that seem reasonable? It's actually called that for the opposite reason. Because you can fix it. You can remove this discontinuity easily by just defining it. See here, there's nothing I'm going to be able to do to fix this easily, right? Like the whole function is just jacked up. It's going to infinity. I would have to somehow make these come together, and then it wouldn't even be the same function, right? This one, I couldn't fix this one because, again, I would have to somehow bring these 2 together, and that would change the function completely. This one, easy fix. Define the function at 2 to be that number, and I'm done, right? And just fix it. Remove the discontinuity. All right, now we also have an idea of left continuity and right continuity. And I'm not going to get into like reading this all out. I'm going to show you in pictures. Is this function continuous at 2? No, right? No. Now, let's discuss left continuity at 2. At 2, if I just look from the left side coming in, is it headed towards something? Yes. Now, is where it's headed to also the function's value there? Yes. So this would be considered to be left continuous. Is it right continuous? So now if you come into the right, is it headed somewhere? Yes. But is it headed to the actual function's value? No. So this would not be right continuous. Right continuous. Left continuous? No. Now, continuity on an interval. We were talking about continuous at points, right? But what if your function is continuous on every point inside some interval? So look at this one right here. Do you agree that between 1 and 3, every point I could pick in here, I would be continuous? The question becomes, what about the endpoints? What about at 1? Am I continuous there? Well, for continuity, don't you have to be coming in from the left and the right? Right? But over here, I don't have a graph, do I? And over here at 3, from the right, I don't have anything, right? So how can you say it's continuous at these 2 points when you don't have, you're missing like halves, like sides? Agree? You know what I'm saying? Okay. Well, it's okay, because if your function is defined on an interval like this, at the left endpoint, you only have to be right continuous. And at the right endpoint, you only have to be left continuous, and you can still say it's continuous at these 2 points. It's like a special case. If your domain is restricted, then if you want to talk about continuity at the endpoints, you only have to consider one side continuity. That way we can still call it continuous. All right, let me see here. Yeah, this is important. All right, so this is just a bunch of results. If you have 2 functions, f and g, that are both continuous, you can draw them without picking up your pencil. Then if you add or subtract the functions together, it's still continuous. If you multiply it by a constant, it's still continuous. So like, think about the sine function. Does the sine function seem like it's continuous? Yes? If you scale the sine function, multiply it by 2, it just stretches out the amplitude, it's still continuous. That's what this is saying. And then if you multiply 2 functions that are continuous together, it still remains continuous. And if you divide 2 functions together that are continuous, it's still continuous so long as the denominator is not 0. And we'll finish up with this. We have to do some examples, but this is just so you know. Every function you studied in college algebra, all the polynomials, quadratics, cubics, all those were continuous everywhere. All rational functions, which had those vertical asymptotes and stuff, are continuous everywhere? No. Right? Rational functions had like vertical asymptotes, and they could do like crazy things like this, and they could do that, right? And we obviously cannot pick this or draw this without picking up our pencil, right? This is saying that all rational functions are continuous on their implied domains. So if you just look like between these 2 dotted lines, everything in there, that's continuous. And everything over here, that's continuous. And everything over here is continuous. So on it, their implied domains, they're nice continuous functions. Same with all of the 6 trigonometric functions. On their implied domains, sine, cosine, tangent, cotangent, cosecant, secant, all of them are continuous. And that's it. We'll do a little bit more of this. We have to do some examples in here. So we're not done with this section. You should now be able to do all the homework for 1-6. Did you all see I emailed out? Did I email it?
Yeah, you did. Yes.
The calendar now has all the homework assignments. So 1-6, get it done. You can start 1-5 if you want, but we're not done with this section. Have a good day.